Magnetic induction could be the source of the odd voltage readings. If a conductor is in close proximity to live wires, it can have voltage induced within it. This is more prevalent when wires are run parallel and close to each other. Secondly, a ground loop can create unusual voltage readings. If metal raceways or boxes are not properly grounded, voltage can be induced on a conductor due to a difference in potential between the grounded and ungrounded conductors. Thirdly, an improper neutral connection or open ground can lead to the issue. A white wire entering a switch box improperly connected or disconnected from the neutral bus in the main panel can cause voltage to appear on the conductor if it is somehow connected to the grounding system. To properly troubleshoot, you can take these steps. 1. Disconnect the conductor from the switch box and from the fixture. 2. Check voltage readings. Measure the voltage between the grounded conductor and the ungrounded conductor, and also between the grounded conductor and the suspected conductor. 3. Test raceway continuity. Use a continuity tester to ensure the raceway is properly grounded and that there are no breaks or disconnections. 4. Verify the neutral connection. Make sure the white wire in the switch box is properly connected to the neutral bus in the main panel. By following these steps, one can narrow down the potential cause and take corrective actions. Magnetic induction occurs when a conductor is exposed to a changing magnetic field. This field induces a voltage in the conductor proportional to the rate of change of the magnetic field and the length of the conductor within the field. The induced voltage can then cause a current to flow if the conductor is part of a closed circuit. Ground loops are unwanted currents flowing through the grounding system of an electrical circuit. They occur when there are multiple paths to ground, creating a loop. This can happen due to improper grounding practices, such as connecting multiple ground wires to different points in the system, creating a difference in potential. The difference in potential drives current through the grounding conductors. This current can cause noise and interference, and in some cases pose a safety hazard. An open ground occurs when the grounding conductor is disconnected or broken. This eliminates the path for fault current to flow back to the source, which can prevent circuit breakers from tripping in the event of a fault. Without a proper ground, electrical equipment is more susceptible to damage from surges and electrostatic discharge. An improper neutral connection occurs when the neutral conductor is not properly connected to the neutral bus in the main panel. This can result in voltage imbalances and equipment malfunction. It can also create a shock hazard, as the neutral conductor may carry current that should be flowing through the ground conductor. When troubleshooting, it is important to use proper safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and using insulated tools. Always turn off the power to the circuit before working on it, and verify that the circuit is de-energized with a voltage tester. If you are not comfortable working with electricity, it is best to call a qualified electrician. Continuity testing is performed with the multimeter set to the continuity function, which usually has a diode symbol or looks like a sideways speaker. This setting emits an audible tone when a circuit is complete. Before testing, ensure the circuit is de-energized. Touch the meter probes together to confirm the meter is working and that you hear the audible tone. Then place the probes across the points you want to test for continuity. If the meter beeps, there is a continuous path. If it does not beep, the circuit is open. When testing a raceway for continuity, place one probe on one end of the raceway and the other probe on the other end. The meter should beep, indicating a continuous ground path. If it does not, inspect the raceway for loose connections, corrosion, or damage. Also, check any bonding jumpers that connect sections of the raceway together. Voltage testing is performed using a multimeter set to the appropriate voltage range. When testing for voltage, start with the highest range and work your way down until you get a clear reading. This will help prevent damage to the meter if you are unsure of the voltage level. To measure voltage between 2 points, place the meter probes on those 2 points. The meter will display the voltage difference between them. When testing for voltage between a conductor and ground, place one probe on the conductor and the other probe on a known good ground, such as a metal water pipe or a grounding electrode. The meter will display the voltage between the conductor and ground. When working with electrical circuits, it is important to understand the different types of conductors and their functions. The ungrounded conductor, also known as the hot wire, carries the electrical current from the source to the load. The grounded conductor, also known as the neutral wire, provides a return path for the current back to the source. The grounding conductor, also known as the ground wire, provides a path for fault current to flow back to the source in the event of a fault. This helps to trip circuit breakers and prevent electrical shock. The National Electrical Code, or NEC, provides guidelines for safe electrical installations. It covers topics such as wiring methods, grounding, overcurrent protection, and equipment installation. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. When working with electrical circuits, it is important to follow all applicable codes and standards. This will help to ensure a safe and reliable electrical system. Flexible metal conduit, or FMC, is a type of flexible metal tubing used for electrical wiring. It is often used in locations where rigid conduit is difficult to install, such as in tight spaces or around bends. FMC is typically made of aluminum or steel and is available in various sizes. It is important to use the correct size FMC for the application and to properly support and secure it. When installing FMC, it is important to use approved fittings and connectors. These fittings provide a secure connection between the FMC and the electrical boxes or equipment. They also help to protect the wires from damage. When cutting FMC, it is important to use a proper cutting tool, such as a cable cutter or a hacksaw. After cutting, it is important to deburr the cut ends to remove any sharp edges that could damage the wires. When pulling wires through FMC, it is important to use a wire lubricant to reduce friction. This will help to prevent damage to the wires and make the pulling process easier. It is also important to avoid overfilling the conduit with wires. The NEC specifies the maximum number of wires that can be installed in a given size of conduit. When working with metal electrical boxes, it is important to ensure that they are properly grounded. This can be done by connecting a grounding conductor to the box using a grounding screw or clip. The grounding conductor should then be connected to the grounding system of the building. It is also important to ensure that the metal boxes are properly bonded together. This can be done by using bonding jumpers to connect the boxes together. The bonding jumpers should be sized according to the NEC. When installing electrical boxes, it is important to use the correct type of box for the application. There are different types of boxes for different wiring methods, such as non-metallic sheath cable, armored cable, and conduit. It is also important to choose a box that is large enough to accommodate the wires and devices that will be installed in it. When installing devices in electrical boxes, such as switches and receptacles, it is important to follow the manufacturer's instructions. The devices should be securely mounted in the box and the wires should be properly connected. It is also important to ensure that the devices are properly rated for the voltage and current of the circuit. When making wire connections, it is important to use the correct type of wire connector. There are different types of connectors for different types of wires and applications. It is also important to ensure that the wire connectors are properly sized for the wires being connected. The wire connections should be tight and secure to prevent loose connections, which can cause overheating and fires. When working with electrical circuits, it is important to be aware of the potential hazards. Electrical shock is a serious hazard that can cause injury or death. It is important to avoid contact with live electrical parts. If you must work on a live circuit, use extreme caution and wear appropriate personal protective equipment. Electrical fires are another potential hazard. They can be caused by faulty wiring, overloaded circuits, or damaged equipment. It is important to have a working smoke detector in your home and to test it regularly. If you suspect an electrical fire, turn off the power to the circuit and call the fire department. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When the current in a circuit exceeds the rating of the overcurrent protection device, the device will trip, interrupting the flow of current. It is important to use the correct size overcurrent protection device for the circuit. Using a device that is too large can allow the circuit to become overloaded, which can cause overheating and fires. Using a device that is too small can cause nuisance tripping. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electrical shock. They work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current, it indicates that current is leaking to ground, which could be through a person. The GFCI will then trip, interrupting the flow of current and preventing electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are designed to protect against electrical fires. They work by detecting arc faults, which are small electrical sparks that can occur in damaged wiring or loose connections. The RFCI will then trip, interrupting the flow of current and preventing a fire. RFCIs are required in certain locations, such as bedrooms and living rooms. When working with electrical circuits, it is important to have a basic understanding of electrical theory. Voltage is the electrical potential difference between 2 points. It is measured in volts. Current is the flow of electrical charge. It is measured in amps. Resistance is the opposition to the flow of electrical charge. It is measured in ohms. Ohm's law states that voltage equals current times resistance. This law can be used to calculate the voltage, current, or resistance in a circuit if the other two values are known. Power is the rate at which electrical energy is used. It is measured in watts. Power equals voltage times current. This formula can be used to calculate the power consumed by a device if the voltage and current are known. In alternating current, or AC circuits, the voltage and current are constantly changing direction. The frequency of the AC voltage is the number of times per second that the voltage changes direction. In the United States, the standard AC frequency is 60 Hz. In direct current, or DC, circuits, the voltage and current flow in one direction only. Batteries are a common source of DC voltage. When working with electrical circuits, it is important to use proper wiring techniques. Wires should be properly sized for the current they will be carrying. The NEC provides tables that specify the minimum wire size for different current ratings. Wires should be properly insulated to prevent electrical shock. The insulation should be rated for the voltage of the circuit. Wires should be properly connected to devices and equipment. The connections should be tight and secure to prevent loose connections, which can cause overheating and fires. When running wires through walls or ceilings, it is important to protect them from damage. This can be done by using conduit or cable protectors. Wires should be properly supported to prevent them from sagging or becoming damaged. When working with electrical circuits, it is important to use proper grounding techniques. All metal parts of the electrical system should be properly grounded to prevent electrical shock. This includes electrical boxes, conduit, and equipment. The grounding system should be connected to a grounding electrode, such as a metal water pipe or a ground rod. The grounding electrode should be buried in the ground to provide a path for fault current to flow back to the source. When working with electrical circuits, it is important to follow all applicable codes and standards. This will help to ensure a safe and reliable electrical system. It is also important to consult with a qualified electrician if you have any questions or concerns about electrical work. In residential wiring, common voltages encountered are 120 volts and 240 volts. 120-volt circuits are typically used for lighting, receptacles, and small appliances. 240-volt circuits are typically used for large appliances, such as electric stoves, clothes dryers, and air conditioners. In commercial and industrial wiring, common voltages encountered are 208 volts, 277 volts, and 480 volts. 208-volt circuits are typically used for lighting, receptacles, and small equipment. 277-volt circuits are typically used for lighting in large commercial buildings. 480-volt circuits are typically used for large equipment, such as motors and air conditioners. When working with different voltage levels, it is important to use the correct type of equipment and wiring. The equipment and wiring should be rated for the voltage of the circuit. It is also important to follow all applicable codes and standards. When troubleshooting electrical problems, it is helpful to have a basic understanding of how electrical circuits work. A simple electrical circuit consists of a voltage source, a load, and a path for current to flow between them. The voltage source provides the electrical potential difference that drives the current through the circuit. The load is the device that consumes the electrical energy, such as a light bulb or a motor. The path for current to flow is provided by the wires and conductors in the circuit. When the circuit is complete, current will flow from the voltage source through the load and back to the voltage source. If the circuit is broken, the current will stop flowing. Electrical circuits can be wired in series or parallel. In a series circuit, the components are connected end to end, so that the current flows through each component in turn. In a parallel circuit, the components are connected side by side, so that the current has multiple paths to flow through. When troubleshooting electrical problems, it is important to use a systematic approach. Start by identifying the symptoms of the problem. Then gather information about the circuit and the equipment involved. Next, develop a hypothesis about the cause of the problem. Then test your hypothesis by performing measurements and observations. Finally, repair the problem and verify that the repair was successful. When working with electrical circuits, it is important to be aware of the potential for electromagnetic interference, or EMI. EMI is unwanted electrical noise that can interfere with the operation of electronic equipment. EMI can be caused by a variety of sources, such as electrical motors, radio transmitters, and computers. To minimize EMI, it is important to use shielded cables and connectors. Shielded cables have a metallic layer that surrounds the wires, which helps to block EMI. Shielded connectors provide a secure connection between the shielded cables and the equipment. It is also important to ground the equipment properly to provide a path for EMI to flow to ground. When working with electrical circuits, it is important to be aware of the potential for electrostatic discharge, or ESD. ESD is the sudden flow of electrical charge between two objects. ESD can damage sensitive electronic components. To minimize ESD, it is important to use ESD-safe practices. This includes wearing ESD-safe clothing, using ESD-safe mats, and using ESD-safe tools. It is also important to handle electronic components carefully to avoid generating static electricity. The NEC table 310.16 provides ampacity ratings for conductors. Ampacity is the maximum amount of current that a conductor can safely carry without overheating. The ampacity of a conductor depends on the size of the conductor, the type of insulation, and the ambient temperature. It is important to use conductors with sufficient ampacity for the current they will be carrying. Using conductors with insufficient ampacity can cause overheating and fires. The NEC table 250.122 provides grounding conductor sizing information. Grounding conductors are used to connect metal parts of the electrical system to ground. The size of the grounding conductor depends on the size of the ungrounded conductors in the circuit. It is important to use grounding conductors of sufficient size to provide a path for fault current to flow back to the source. Using grounding conductors of insufficient size can increase the risk of electrical shock.